In this video, I will guide you on like how to solve the dep-1, 2, and 3. So after fetching week 4, you can see the subdirectories dep-1, 2, 3, and stack cookie 1, 2, 3, 4. And then we will have another video for the tutorials for the stack cookie. So this video is just for dep-1, 2, 3. Let's start with the dep-1. And then you can check the source code of the dep-1 at here. But please use the source code as a guideline for your reverse engineering. So that is, to get the exact address of the exact location of the buffer address and relative to ESP or EBP, you need to take a look at the assembly lines. For example, we don't know where this buff is at in the relative location to EBP. So for example, EBP minus 0x88. So we are not sure about that size. So this is just the source code, and the actual representation that CPU runs is in a binary format. So you need to check the binary to get the exact location for the address for the buffer. And you guys have already experienced that, like the having a wrong address a little bit. Yeah, that could affect a lot on exploit writing. So that's important. So the structure of the challenges will be very similar to all the challenges in week 4, and it starts with the main function and it will inherit the permission. So please check that if the challenge inherits permission for you or not. If this line is missing in the challenge, then you need to run your own set regid. Otherwise, you can just ignore it and just focus on the running a shell command. And then internally it runs a non-main function. And in the non-main function, what it does is just calling an input function. And the reason why we have a main and non-main function and then another input function is that I will let you do like the full, let you have a full freedom for like launching the EBP attack, the frame pointer attack, and then that requires a dep-2 for the return. And then if you solve the level 9 of the week 2, then you realize that why I nested into 2 levels, because like the main function returns differently over ECX something. So you will not have getting a trouble in launching the frame pointer attack in input function. And that's for your convenience, and then you don't have to exploit that if you can do it in a more simple way. And then in the input function, we have this read function. What it does is like that it reads some of the data from standard in, which is a file descriptor 0, and then we will put the data into the buffer. But the current buffer size is a buff size, but our read function reads twice size of the buff size. So there will be a buffer overflow, and your job is to exploit that. And previously we learned about like we can call some of the functions, or we can also call some of the the shellcode. We can upload the shellcode in the executable area, and then we can jump to that. But the reason why this challenge is called the DEP is like I applied the data execution prevention to the binary program. And to check that, you can use the command pawn checksec and then binary name. Then it will kindly show that the architecture is a 32-bit little endian, and then it will show whether there's some other defense mechanisms are available or not. And then most importantly, it says NX enabled. So non-executable stack is enabled to this binary. And then to check this more manually, you can use the command read elf -a, then the binary name, and then grep stack as a capital letters. Then you will see that the GNU stack is marked as a read writable but not executable. So in this case, even if you upload your shellcode to somewhere in the stack, for example, environmental variable or argument or file name, you can jump to there, but you cannot execute the shellcode. So it will generate the segmentation fault right after you jump to the stack, because the memory permission for that is marked as a non-executable. And then that is enforced since 2004, after the hardware designers such as AMD and Intel implemented the NX bit, non-execute bit, in their page table. So right now our challenge is that we know there is a buffer overflow vulnerability, but we cannot inject the shellcode, and the function that we have is this function, sum function. And then we will just practice the calling this sum function to exploit the vulnerability of the dep-1. And let's just try it. Maybe you may be curious about like how can you get launch the general shell and the cat flag out of it. But I will just first call this sum function for the exploit. To do that, let's check this assembly of input function first. Then there's a read function. Then last push is the file descriptor. The second last push is the buffer, and then buffer is coming from EBX, and that's at EBP minus 0x88. Now we know that the buffer is at here, so let's write an exploit script. So we'll open dep-1, and then we know that the buffer is at here, and it's some message that we receive, and then we will prepare buffer, and then 0x88 to fill entire buffer, and then la to fill EBP, and then we can change EIP here. And then the function that we are interested in is sum function, and then we can get the address of the sum function from this dictionary, and then p32 sum function. By doing this, we can call sum function by exploiting the buffer overflow vulnerability. There's no problem at all because sum function is mapped in the already executable area. And if you are curious about like what kind of the addresses are executable in the executable area, you can check it on GDB by running the program. So let's break a main and then run the program. And after doing this, if you type the command bmmap, it will show the virtual memory map of the program. So for example, from the address 8048.000 to 9000, these addresses are read, non-writable, and executable. And this is actually the code section of the dep-1 binary. And then there's a data part of the dep-1, and then it's marked as a non-executable, non-writable because it's a read-only data. So it will store some of the string literals. For example, we use some of the messages on printf or something. So this read-only data is stored into this area. And then definitely there's a read-writable data area for the binary 2. So read-writable but non-executable. So for a ELF binary program, you can safely assume that there will be at least one executable area, which is a code section, and then at least one read-only area, which is read-only data for read-only data, and then at least for like one read-writable area for storing the global variables that are writable. Yeah, and then that kind of the assumption applies to the another binary programs. For example, here's a libc2.23. So this is a standard C library, and it contains all the code for printf or system or scanf, those kind of the functions that you use, but they're not implemented by yourself. Yeah, these are in this area, and then this is also the code section, and then read-only data and read-writable data. Same thing happens for the LD. So read and executable area for the code, and then read-only area for the read-only global variables, and then read-writable area for the writable global variables. And then our stack finally, it says stack is from here to there, and then read, write, but non-executable. Yeah. And then where the sum function is. So sum function is a 80485553. So it's in this area. That's why it is a read and executable. So it's executable. So we can execute this function. And then after having the script like this, then we can send buffer to the program and check the output. So it has been executed, but the problem is that, so what we just did is we executed this sum function, and what it internally do is that it will execute system ls. So ls is something like this, and that's why if we jump to that sum function, it will run ls and then just print this information. That's it. Then how can we run sh out of this function? Yeah, that's the hidden challenge of this one. So the first door to the first hurdle that you need to pass is like the run sum function from the binary, and then second part of the challenge is that you need to change your environment to execute the shell, not the ls command at here. And to do that, let's think about like how your command line can find the executable and run the program. For example, we have an editor vim. Then, do you know where this vim program is located? It is not in your directory at all. Yeah. And if we do which vim, then it will let us know that where the vim program is. Then it's under the user bin vim directory. And how your shell automatically finds like where your program is from the environmental variable called path. So basically what your shell is doing is like if you type a command, then it will search for your command vim from this directory first. If there is not, if it does not exist in this directory, then moves to the next, moves to the next, moves to the next, then found the user bin vim, then it will run the program. So this variable actually controls like the how your program name could be found in the sum of the directory, and then determine like the which program to execute. So in that case, if we set our path as, so for example, this current directory first. So path search is sequential from head to the tail, and then separated by the colon. So if we add // at the head, then it will search for the command from our directory first, then search for the, where is ls? Bin ls. So for example, when this system command runs ls, if we can make this system runs our ls first, then finding bin ls, then we can hijack that part and then run our own program. So to do that, let's do the first step. So copy bin sh as ls here. So if I do ls, it will still run /bin/ls, because my current path is runs with this. But if we run /ls, then it will just run the shell. So currently, like my shell color is shown like this, but you can ignore that. But the important thing is like we just copied bin sh to ls. So now this ls is sh, and then if we can make this function runs our ls, not the global ls, then problem solved. And to do that, we need to adjust the path environmental variable when we execute this program. And we know that we can create a path environmental variable here, something like this. But after running the shell, we would like to run the sh or cat or some other command to print the flag. To do that, maybe basically we can add some more default path after this one. But the important thing is like // should come first, because by doing that, you will teach the system that the system must find the binary program in our current directory first. Then it will run our ls before searching for the bin ls. And then we need to supply this environmental variable to the process. Then let's run it. So right now, it run our ls, then running the bin ls. So now you got the shell, and then you can successfully hijack the execution and inherit the GID privilege.